All right, this one gets a little messier, guys. Here's the quotient rule. I think I left off the V parts on the last few. Oops, not consistent. The derivative of one function divided by another function. It's not as nice as you want it to be, I'll tell you that much. It's f prime g minus fg prime all over g squared. All right, and where this comes from is pretty wacky. You can look at the proof in the book. It's nothing crazily complicated, but it's a bit tedious and it would take a little bit of time, but it's nothing too bad. I think the worst proof was actually the power rule. And that's only a proof for positive integers when in fact it is true for any exponent. Yeah, this is the quotient rule. And so, first off, or kind of the easiest way to remember this for me is that the numerator is basically the power rule, but now it's with a minus sign. It's basically the product rule, but with a minus sign. And a lot of times multiplication correlates to addition, and division, think exponents, correlates with subtraction. So the numerator is basically the power rule, but with a negative. I've said it again, product rule. The numerator is basically the product rule, and the bottom is just divided by g squared. I don't know. But another way that a lot of people remember it is with this little phrase, low d high minus high d low, square the bottom, and away we go. A nice little rhyme. So this correlates, low is the denominator, high is the numerator, and then d just means derivative. So low, d high, f prime is the derivative of the high function, minus high, d low, square the bottom, and away we go. So I'll be saying that a lot when we do these problems. Do example 5. Find the derivative of the following. Part A is going to be k of x equals 5x squared divided by 4x plus 3. So a lot of times it's really, really helpful to just go off to the side and write your f and g. So f of x is the top function. G of x is the bottom function. And then we need their derivatives as well. Derivative of the first is going to be 10x. Derivative of the bottom, just going to be 4. That's a 4 right there. A 4. Okay. And now we just use a formula. So k prime of x equals low d high minus high d low, square the bottom, and away we go. And now we just replace. F prime of x is 10x times g, which is 4x plus 3. It's multiplying these two together. Minus f of x, which is 5x squared, times g prime of x, which is just 4. It's multiplying those two together. The 4 just can't manage to stay out from underneath my webcam. Divided by the denominator squared. 4x plus 3 squared. All right. And now we just have to simplify. So the first thing we have to distribute, that's going to be 40x squared plus 30x minus 20x squared. The denominator is going to be 4x plus 3 squared. Again, a lot of times when you're simplifying fractions, a lot of times when you're simplifying rational expressions, it's useful to leave the bottom factored. Sometimes we have to FOIL out the bottom, but usually we leave it factored. Collect like terms. We have a plus 40x and a minus 20x squared on both of them. It's going to be 20x squared plus 30x. And the last thing to do when simplifying a rational expression is to factor everything and cancel if you can. So the biggest thing that we can factor out is a 10x. And what we're left with is just a 2x plus 3. Oh, it almost cancels. And we have a 4x plus 3 in the bottom. But even though they're close, the bottom doesn't factor anymore, the top doesn't factor anymore, and none of these factors are the same. This is actually as simplified as it can get. All right, so you have to be a little careful with these ones. This is the answer. This is the form that your final answer should be in. Let's do another one. Find the derivative of this function, 3 times h of x plus x squared over g of x. And you might say, Jason, how do I find the derivative of this function? I don't even know what these functions are. And the answer is, it doesn't matter. We'll find it anyway. So k prime of x is going to be the derivative of this. We can use the constant multiple rule. Right? The derivative of this is just 3 times the derivative of h. I don't know what h is, but the derivative is going to be h prime. And now we have to use the power rule. Well, yes, part of the power rule, but also the quotient rule. So we go off to the side and say, all right, we want to use a quotient rule. Quotient rule says low d high minus high d low, square the bottom and away we go. And our high function is x squared. Our low function is just g of x. We don't know what that is. Derivative of x squared is 2x, and the derivative of g of x is just g prime. Now we can use this formula. F prime, that's 2x, times g, which is just g of x, minus f, which is x squared, times g prime, which is g prime of x, all divided by g of x squared. And we can factor a little bit, but there's really not much that we can do here. It's going to be 3h prime of x. Again, we want to factor the numerator to see if anything cancels. The numerator, the only thing that we can factor is an x. And we're left with 2 times g minus x times g prime. The bottom, again, is just stuck as g of x squared. So even though this has a g and this has a g, they're two different functions. It's only the notation that makes them look similar. G and g prime might not be anything alike. So even though they look the same, there's no factoring that can happen there. It's just the way we write the derivative. But the derivative sometimes doesn't look a lot like the original function. And sometimes, like with e to the x, the derivative is literally the same function. But that's jumping ahead. Jumping ahead. This is our final answer. How we use a quotient rule here. Let's tie in with some final examples, a couple odds and ends in this section. With example 6. Where does f of x, which equals x cubed minus 7x squared plus 8x plus 1, have a horizontal tangent line? Now, of course, we could just graph this, and we will, but It's a very useful skill for later to be able to find this analytically, find this by hand. Horizontal tangent line. What does that mean? Horizontal tangent line means a slope equal to 0. Specifically, slope is the derivative. So this is just asking where's the derivative equal to 0. Well, let's find the derivative and set it equal to 0. Power rule, 3x squared, combined with the sum and difference rule and constant multiple rules, which we've done a lot here, minus 14x plus 8 plus 0. That's the derivative function. When is this equal to 0? Let's set it equal to 0 and solve. Well, we'd like to factor if we can. There's no common factor. We could use the AC method. We could use a guess and check method. I'm going to use the AC method since this one's a little bit more complicated. Don't think I've mentioned it yet in this class's videos. But we need two numbers that multiply to 24, that add to negative 14. 6 and 4 is close. Wait, I don't think this factors. Sorry, negative 6 and negative 4. Is this supposed to factor? I don't even know. I didn't write that down. X cubed minus 2x. Change it to a minus 2x squared. This is actually going to be... This actually doesn't change anything. I don't think this actually changes anything. So it's minus 2x squared. Now there's a minus 4x. We need two numbers that multiply to 24. That add to negative 4. And yeah, there's nothing. So this doesn't factor. That's okay. There's still ways of solving it. Bring in the quadratic formula. X equals negative b plus or minus the square root b squared minus 4ac all over 2 times a. This quadratic formula is useful for solving when our quadratics equal to 0. Be very careful with your a's, b's, and c's. A is 3, b is negative 4, and c is 8. Plug it in and simplify. Negative b is positive 4. Plus or minus a sneeze. Bless me, sorry about that. Times negative 4 squared, make sure to have the parentheses. Minus 4 times a times c. All over 2 times a. And then we just keep simplifying. 4 plus or minus 16 minus... I've really mucked it up. It's fine, it's fine, it's fine. Minus, is this 96? What are you noticing about this? This is not real. Where is this function have a horizontal tangent line? Nowhere. No real number. Let's look at this cubic function. And you might say, Jason, aren't cubic functions like this? Shouldn't they have horizontal tangent lines like here and here? Come and explore this with me. So let's see what this function looks like. This function looks like x cubed minus 2x squared plus 8x plus 1. And then we're going to have to zoom out a little bit. Negative 10 to 10. Oh, maybe not zoom out quite like this. So we could zoom out even more, negative 100 to 100 maybe. So it never actually gets horizontal. Right? It flattens out a little bit, but it never gets horizontal. So yeah, there is no horizontal tangent line ever for this function. Now, if this were a 7, there would have been 2 of them. If this were a 7, if I didn't change the problem, there would have been 2 answers that we would have also gotten. Wait, this did factor. 2/3 and 4. Huh. Why did I think it didn't factor? I'm losing my mind here. I don't want to spend too much time on this. But when we had 3x squared minus 14x plus 8, this did factor. But we would need two numbers that multiply to 24 that add to negative 14. So they have to both be negative. This doesn't work. Oh. There we go. That's why it's always a good idea to write out everything. Yeah, it did factor. All right, so you could have factored it and solved it, the original problem this way. We changed the problem. Still has some good information for all of you. Let's do one more example. The position of an object in centimeters after t seconds is given by S of t equals t over t squared plus 1. I hope y'all noticed that that one factored and you were like, Jason, come on, it's -2 and -12. All right. This is our position function. And the question is, what is the initial velocity? Well, to answer the question, we have to know what it's asking. What does that mean? Initial velocity. There's two parts, two pieces of data. Velocity, we oftentimes write it as v of t. What's the relationship between velocity and position? The velocity is the derivative of the position. Velocity is just how fast your position's changing. How something's changing, that's a derivative. That's a rate of change. So the velocity is just the derivative of the position function. And initial velocity just means at the start. How much time has gone by at the start? None. It wants the velocity when t is equal to 0. So let's find the velocity equation and then plug in 0. So s prime of t, which is the same as v of t, is the derivative of this rational function. Well, okay, we're going to have to use the quotient rule, where the top function, f of t, is just t. The bottom function, g of t, is t squared plus 1. Well, f prime is just 1, and g prime is 2t. So, low d high low times the derivative of the high function minus high d low. And again, we're using t's here because our function is t's, not x's. Square the bottom, and away we go. Now we just plug in what f prime, g, and g prime all are. And we're good to go. F prime is just 1 times g, just t squared plus 1, minus f, which is t, times g prime, which is 2t, all over t squared plus 1 squared. Now, if I actually asked you, find the velocity function, you'd have to keep simplifying this. But we only care about the velocity after 0 seconds. And in fact, we didn't even need all of this. We could have just used f at 0, g at 0, f prime at 0, g prime at 0. We only care about at 0 in this case. So it's good practice if you want to keep simplifying. But specifically, we really only do want the value at 0. So we can save ourselves a little bit of time by saying, all right, this is our velocity. So specifically our velocity after 0 seconds, just plugging in 0 here. Plug in 0 to the first thing, you get 1. Plug in 0 in the second thing, 0 times 0. Plug in 0 on the bottom, 1 squared. In other words, it simplifies to 1. The initial velocity is 1 miles per hour, meters per second. What are our units? It's a rate of change. So it's going to be in units of s divided by units of t, or centimeters per seconds. Moving 1 centimeter every second, not very fast. Unless it's a really, really tiny object, and then I guess 1 centimeter per second is faster, but not very fast. All right, and that's this video. Let me know if you have any questions, and good luck.